sheets.
All right, so just a quick comment on how to use F0. So I'm just gonna do help F0 quickly to see what MATLAB says and whether it's helpful. So the problem with MATLAB help is that it's always very verbose. So reading through it is not necessarily simple. But basically you need to have a function or some way to define it. Okay? And you need to have a starting point. Okay? So basically at the very minimum, you don't know which algorithm F0 will use. Okay? It will use a range of algorithms. But basically X0 basically implies that it's going to probably be one of the open methods. Newton's method, fixed point iteration, and so forth. Now, let's try with this function. So the simplest way would be just using, so I think whenever you're confused how to use something, so sine function is something that does have a MATLAB file, okay, that tells you how to compute sine of x. Okay. So that MATLAB file exists somewhere in MATLAB storage, but MATLAB knows how to find it. So if I actually do this, so I'm just going to control that, Control C. Whoops, that's not what you can see who I was emailing just before. So I'm just going to do F0 of at sine and 3. So I know that sine pi is 0, right? Sine 0 is 0, sine pi is 0, sine 2 pi is 0, and so forth. So close to 3, my closest root for sine function to 3 is pi, 3.14. Right? So I got the answer. Yes?
What does the at sign do?
So it's really, so what it means by that function, it means a pointer to the, so take that, don't take it as sin word or name of a variable, take it as a function.
Okay.
Okay? So it's telling it this is actually a pointer to the function. Okay. So interpret this as it's essentially telling MATLAB to look for .m file, sine.m, somewhere in there. Okay. And this is 3. Now if I actually had, so this is when I actually have a function that is defined by MATLAB, okay? What I could do is I could define my own, okay? And the simplest way is I could define my own like this, if just this is so-called defining it inline, and I'm gonna do a simpler version of it. I'm just gonna do x plus 1. What is root of x plus 1? X plus 1 equals to 0. X is minus 1. Okay? So I'm going to start from minus 2. Okay? So this is telling, okay, interpret this as a function of x. Okay? Basically, whatever comes here, interpret as a function of x. Okay? Oh. Did I? Apparently, it's not tolerant of any spaces. So this is interpreted as a function of x. My starting point is minus 2. I could also have my function, instead of sine function, I could have a .m file, and then I would behave the same. I would just give it the name of .m file. And there's one more useful thing, is that you can actually say, this is inline definition of a function. So this is, I'm defining my function in one line. I could also have an entire file doing it as a function of x and c, and all it does is doing cosine of c times x. Okay. And then if I'm looking for zeros, okay, it's gonna search, it's gonna interpret this function only as a function of x, and c is something that is set. Okay, so that's something that I could actually do separately. Yes?
So when you set your starting point, what good is the starting point? What does that do?
So that sets that x0 in Newton's method. I gotta start from somewhere. So every root finding algorithm, I have to start from something. I have to initialize where I'm starting my search.
Okay.
So that point that you specify as x0 is your starting point of your search.
Okay.
And algorithms are sensitive to that starting point. If you have a sine function, back to the sine function, okay? If you have a sine function, okay, you could do search close to 1, okay? And I'm going, this is effectively 0, okay? So I'm going to a different route based on the starting point.
Okay.
So I'm typically looking for the closest route.
So if I did 5 instead of 1, then we just go to 2 pi.
Yep. Now somewhere in between, okay? This one went to 0 effectively, pi over 2. Now let's try this. Pi over 2 times 1.1. So that one went to pi. Slightly over, and that's because I'm right near the peak where my sine function is maximum. So little on this side, I'm going to go to 1. Little on the other side, I'm going to go to pi.
With an equation, you can use like x plus 1, you can kind of determine where to have the starting point, right? So for an equation, you can't tell where the zeros might be.
You got to try. It's trial and error, and you might fail. Yeah.
You should graph it.
Graphing is helpful. So this is actually, I know how sine looks like. So I know that it's a 0 at 0, 0 at pi, and at pi over 2, it's maximum. And right around that maximum, if I'm a little below, I'm going to go to 0. If I'm a little above, I'm going to go to pi.
The x is kind of confusing over here, isn't it? By default, like,
This
when you had.
This is a function that is defined by MATLAB, and it has only one input, so it's not going to be confused.
No,
Which
but I'm just saying when you put x instead of sine something, like a little below, you had that x plus 1 minus.
Yes. That's just taken as a variable. So I'm defining a function right there.
But if you had like an x file like in your
Then you would just say et in name of that file. If it had one variable, then it's no problem. Okay? Does that answer questions for homework? All right. So I actually gave, today we're switching or continuing our discussion on linear systems, and actually something that we already went over. Does everybody have a worksheet? Everybody has a worksheet? All right. So open up the worksheet, and I actually want you to work on it during the class. Let's see, where's my worksheet? So it looks something like this. And we already introduced our linear systems, so this is continuing our lecture 6 on linear systems. This is something that should be a review of what you did before. So there are two systems and two unknowns. Let's solve them by hand. And if you're done with that one, you can move on to number 2, sketch the solution of the system. So I just gave you sort of a grid to work with. You can draw however you'd like on that grid, but it's just to help you draw lines. So did everybody complete first two? How do I draw a line? Any line. I need to identify 2 points on a line to actually draw a line, right? So since you have the equation, you can do that. Okay. Never mind. Second here. The software is torturing me here. Okay. Okay. So what did you get for the system of equations? It was 3. Whoa, hi. It was 3x 1 plus x2 is equals to 7, minus 3x1 plus 2x2 is equals to minus 4. There's multiple ways to solve this. One way would be just to add these two together. So I'm going to get that 3x2 is equal to 3. So my x2 is equal to 1. Correct? And what is x1 then? 2. So there is a unique solution to this system. Okay. This actually happens often when I hook up my computer to the projector using that other alternate line, and I have one more device asking for some space there or something. MATLAB says, I quit. I cannot deal with this demanding system. All right. Now, how would I plot this? I will give myself something like this. Okay. So I have one line. So this first line, it's going to have one point is obviously 1, 2, and I'll give myself another point if I plug in x1 as a 0. What is my x2? If x1 is 0, what is x2? Seven. So I just plug in x1 as 0. So this is my x1, my x2. So I will have, let's say that this is 1, this is 1. So 1, 2 is this point, and 0, 7, 2, 3, 4, 5, 6, 7 is right here. So my line is something like this. And my other equation, one point is obviously this 1, 2, and another point, if I plug in, it's 0 and minus 2. Okay. So somewhere here. Okay. So I'll have something like this. And of course, I cannot draw a straight line through 2 points. But you get the idea. It's an intersection of 2 lines. So 2b, in this x1, x2 plane, the solution is a point, 1, 2, at the intersection of 2 lines, right? Now, if I had 3 equations, this is a comment I made at the end of the class last time, what would happen in 3D? Of planes. So I'm intersecting planes, and the plane in 3D looks something like 3x1 plus x2, let's say minus x3 is equal to 2. I'm coming up with numbers. What is a normal to this plane?
The dot product of the coefficients is 0.
Right, so basically my normal is 3, it's a vector 3, 1, minus 1 in 3D. Every plane has a normal and a point it passes through. Okay. So this normal is visualized as this coefficient with x1, so 3, 1, minus 1. Yes?
Why is it the intersection of 2, 1?
It is, because I wasn't paying attention. All right. This is actually 2, 1. So I drew this incorrectly. I was just reading 1, 2 without. All right. I love the eraser on this thing. All right. So this point is still staying minus 2. And it's actually 2, 1. Okay, so it's this. I just drew 2 different types of lines, that's all. And the other one is 0, 7, so that was somewhere here. All right. Now, why don't you, yes?
Sorry, I have a question for C. So if there's a system with three equations, if we're gonna know the solution would be a line.
No, it would still be, so if I'm intersecting two planes, it's going to be a line. But three planes, it's still going to be a point, if there is such a point, okay? So it's still going to be a point in 3D at the intersection of three planes, if I actually had that unique solution. Now, of course, if I have parallel planes, I'm not going to. This is just for visualization, for your information. The normal to this plane is 3, 1, minus 1, or whatever coefficients you have here. Okay. Now, number 3, it's asking whether three x1 plus x2 is equal to 7, and minus 3x1 minus x2 is equal to minus 7. Does it have a solution? And where is it graphically on this plot that we just sketched? And another one is 3x1 plus x2 is equal to 7, and 3x1 plus x2 is equal to 5. So I also invite you to actually plot these two lines, these added. So 3x1 plus x2 is equal to 7. That one you already have, it's in red. Where are these other two? In A and B. And if you're done with that, keep going to page 2. Do not sit bored. That's a capital offense. Yes.
For the intersection of three equations,
Uh-huh.
3D plane, the solution would be a line as well.
It could be if two of those planes collapse to the same thing.
Speaking of having two planes like this,
If you have two planes parallel, like that?
and then another plane like this, it going through the middle.
it's still going to be a point unless two of those are somehow coinciding. If two planes collapse into the same thing, then it's going to be a line. Intersection of two planes is a line. I cannot intersect three planes in a line unless two planes are actually the same thing. 2 out of 3. Not. There are 3 papers. Show me. Well, he's arranging papers. What is the answer here?
Same line.
It's the same. I can actually see that these points that I had here, this is 2, 1. Two, 1, and 0, 7 are still on this when I draw the same thing. So this is same. This is sort of some weird equal or equivalent. Whatever number I multiply this equation with, it's going to stay the same equation. And in this other case, where is this one compared to this one? They're parallel, right? I'm gonna draw it in green. So this one is going through 0, 5. Okay? And also 2 below here. So it's actually something like this. So is there a solution?
No.
No. So here, the solution is entire line. Okay? The solution is entire line. So there's infinitely many. And here, there's no solution. Because otherwise, 7 has to be equal to 5. And 7 is not equal to 5. Did we manage to read? Oh, okay, so they could be, yeah, they could, but then, okay, let's go back. It's still 2 of them have to, so one of those planes is a linear combination of the others. They're not the same thing, but it's like 2 times first equation plus third equation. Yeah. So they're linear, it's called linearly dependent. So what they were wondering is like, could I have 3 planes passing through the same line? Yes, I could. But 2 of those planes, then somehow I can linearly combine as I take coefficient times the first one plus coefficient times the second one and get the third. Okay. So move on to the next page, and why don't you all work on 4 and 5 before I get to it. And again, if you're bored, you just proceed to five, 6. So how do I represent this as a system? I want a matrix times a vector is equal to vector. Based on what you know about multiplying matrices. What is this matrix here? I'm calling it A. Coefficients, so 3, 1, minus 3, 2. And my vector is x1 and x2. That's what I'm looking for. So when I multiply these two, in the first, as a first element, I'm going to have 3x1 plus x2 is equal to 7. And minus 3x1 plus 2x2 is equal to minus 4. So this is my matrix of coefficients. This is my right-hand side B. Now if you open MATLAB, which crashed on me, so I'm not going to do it right here. What do you do if you type in A/B?
Error.
A/B. Did you type in A? Did you type in B? And you got an error?
Oh, it has to be the other slash.
Ah, the other slash. There's a backslash this way, back. Ah.
What's the difference?
When I'm multiplying or dividing, in this case, matrices, I can do it from the left or from the right. Remember the matching dimensions? So A times B is not the same as B times A in matrix multiplication. So when you flip your backslash, you're trying to multiply the other way. So effectively what you were doing, you were trying to solve Bx is equal to A. Okay? And Bx is equal to A, B and X being both vectors doesn't work out in matrix multiplication. Alright. So point of A/B is that MATLAB is smart and it has an algorithm underneath that solves this system of equations. Now in 2D that's not a problem. For multiple dimensions it's not so easy, and what we are going to do as first part of this class is learn how to solve the systems. I trust you probably learned that in linear algebra, but I'm reviewing it anyway because we'll need to program it. So I gotta review it anyway. So let's actually do some, so number 6, have you started? In number 6, we have a simple system where A, 1, 0, 0, 0, 3, 0, 0, 0, 5. Now I actually have 3 x's is -1. And I also have so first work on solving those yourself. Yes, they're 3 by 3, but they're actually somewhat simple. And let me know when you're done. So what is the solution in first case? What is my x1? So it's kind of the equation, the first equation is really simple because it's actually 1 times x1 is -1, so x1 is -1. Second equation is 0 times x1 plus 3, x2 is equal to 6, so x2 is equal to 2. And 5, x3 is -15, so x3 is -15 divided by 5 is equal to -5. So this is so-called diagonal matrix. I do not do basic operations today well. It's a Friday. It's rainy Friday. Went to sleep at 2 o'clock. This is what happens. So, all right. Now, how are we going to attack? Did you solve this system? What is the easiest equation to solve here? X3. So that's the one we start with. 4x3 is equal to 8. So my x3 is equal to 2. Now that I know x3, I can plug it in to the equation above. So my 3x2 minus 2 times 2 is equal to minus 1, which gives me 3x2 as 3, so my x2 is equal to 1. Okay. And then finally, I can plug in both x3 and x2 into the first equation. Okay. So I'll have minus 2x1 plus 1 plus 2 times 2 is 4 is equal to 9. 9 minus 5 is 4, so minus 2x1 is 4, x1 is minus 2. So this actually, the moment you actually have a pretty good rule, so A, this is called upper triangular matrix. Essentially, the only elements that are non-zero, what did I do? I don't know, but it's zoomed in. I don't know how to zoom in and out, apparently. I've never done this before. Zoom. Apparently I can move it. Well, that'll work. I'm going to close the sheet in a second. So this is an upper triangular matrix. I have only diagonal and above elements are non-zero, and anything below the diagonal is 0. Similarly, I could have lower diagonal matrix. So when I have a matrix like that, I start from the last equation, okay, solve it, I find that one immediately, and then keep plugging in. And I can actually see a little algorithm in here that I could program as a for loop. That's what you're going to do. 2 classes from now, we're going to do that. Okay. That's called, this algorithm is called backward substitution. Okay. So solve by backward substitution. So I'm not sure what particular method and how you use that in your linear algebra class, or it wasn't a linear algebra class, it was probably within differential equations that you overviewed linear algebra. But I'm actually now going to go through the entire procedure of what we call Gaussian elimination that will take a system that is not necessarily upper triangular, but just a regular system. It's going to convert it to an upper triangular form, and after that we will solve it by backward substitution. And that's going to give us a 2-step algorithm that we're actually going to then implement in MATLAB. Okay. So let's learn how to do that by hand first. So I'm going to place a title Gaussian elimination. So it's a linear system solution procedure that basically first transforms the system into an upper triangular form. And then after that, solve this upper triangular system by backward substitution. There's not one way to do this. Yes, I could actually transform my system to lower triangular system. There's multiple combinations that we could do this in. Maybe you did it slightly differently in differential equations. The point is that I'm just going to give you one algorithm and we're going to implement that one. And after that, you should be able to implement whichever one you'd like. So do you want to start with a 2x2 or a 3x3 system? 2x2 is kind of simple. I don't want you to be bored. 3x3? All right. So let's give ourselves a system. System is minus 3x1 plus 2x2 minus x3 is equal to minus 1. 6x1 minus 6x2 plus 7x3 is equal to minus 7. 3x1 minus 4x2 plus 4x3 is equal to minus 6. First thing, I'm going to work with matrices so I can drop this x1, x2, x3 because I do not want to keep writing it. I'm lazy. So I'm going to form a so-called augmented matrix. And I'm just going to write all of the coefficients in there. First coefficients, my coefficients of A. And I'm going to divide my coefficients of B. I'm going to put them both in the same matrix. Okay. Because I do want to work on B at the same time. If I multiply or modify or do anything to entire row, I need to work both on the left-hand side and right-hand side for my equation. So this is essentially my A, and this is my B. Now, in order to place this system into upper triangular form, what I would do on paper, I would focusing on making this 6 here a 0. And replacing this equation by a linear combination of others. I know already that when I do that from our little drawings, I will not change the solution to the system. So the solution to the system remains intact. So essentially, in order, and what would I replace this with? So I'm going to replace this line, and I'm going to refer to this as first, second, and third row with Roman numerals, so I distinguish them from the regular. So if I do 2 times row 1, I'm going to have minus 6. Plus 6 gives me a 0. So 2 times row 1 plus second row. This transformation, so I'm going to replace this entire second row with this combination. It's called a linear combination. And then I will zero out this first element. Okay? So let's do that. I write my first row all over again. So 2 times minus 3 plus 6 is 0. 2 times 2 is 4, minus 6 is minus 2. 2 times minus 1 plus 7 is 5. And please correct me if I'm wrong. We know already that I cannot do basic operations today. So watch carefully. 2 times minus 1 is minus 2, minus 7 is minus 9. And I'm going to consult my notes. Okay, I'm good. Now, what am I going to do to the third row to basically get rid of this guy or girl? Is 3 a guy or a girl? Do we know? Guy? Okay, 3 is a guy. That makes 4 a girl? No, just kidding. All right, so what am I going to do?
Add row 1.
Add them up. So basically, I'm going to replace my third row by this. So minus 3 plus 3 is 0. That's what I intended it to be. 2 minus 4 is minus 2. Minus 1 plus 4 is 3. And minus 1 minus 6 is minus 7. And then I'm going to focus on this. Is minus 2 a guy or a girl? Just kidding. A girl. All right. So basically now what can I do to this?
Add row 1.
No, if I do row 1, then I'm going to bring in 3 back here. I don't want to mess with that. So I'm now going to work with my second row. Because second row has a 0 here, so it'll do nothing to my 0 that exists. So I suggest that we do negative this row plus this row. That said, I could do negative this row plus this row. I would still achieve the same. Okay? So which do you pick right now? I'm going to squeeze it in here so that I don't do a miscalculation. So maybe negative, and I will write down so I know what I did. So I'm going to replace by minus 2 plus 3. So on test, write down for me, okay? Otherwise, I won't know what you did. So negative is 2 minus 2 is 0. Minus 5 plus 3 is minus 2. And 9 minus 7 is 2. I am now in upper triangular form. So subpoints, there's multiple ways you can do this to create. Your objective is to have zeros below diagonal. Okay? So objective have zeros below diagonal. There are multiple combinations of rows that could achieve that. Kind of when you're solving by hand, you do what seems to be the simplest calculation. We will program later though, and in that case we have to be consistent because we gotta tell the computer to repeat the same thing over again. If you start mixing things up, that ain't good. So the same rule always applies. Okay? All right, backward substitution for this problem. We will continue on Monday. So can you sign these sheets, please? And give them to me? I will return them on Monday.